Welcome to the video Help with Physics Problems for Physics 1B. This video is going to cover Homework Set 6, Part 2, which is everything under the headings Energy Bands, Metals, Insulators and Semiconductors, and Silicon Band Structure, Band Gap, Electrons and Holes. For 1221 students, this is questions 9 to 14. For 1231 students, this is questions 14 to 24, and we'll also cover the extra problems E1 to E3. E4 and E5 are left for you to do. Problem 9 for 1221 or 14 for 1231. In this problem, we're asked in no more than 6 lines, describe the nature of metallic bonds. Well, metallic bonds consist of a positive metallic ion surrounded by loosely held electrons. So we've got a lattice like this of positive ions. And then electrons, which are only loosely held and are free to move. So as the electrons are only loosely bound to the ionic lattice, they are free to move, which means that they can conduct electricity. They are often referred to as a sea of electrons. Okay, and that's an answer to that one. Problem 10 for 1221 or 15 for 1231. In this problem, we're told that the energy gap for silicon at 300 kelvins is 1.14 electron volts. So we've got a conduction band and a valency band. And we've got a gap of 1.14 electron volts between these two. We're asked, find the lowest frequency photon that will promote an electron from the valency band to the conduction band. So we have E is equal to HF is equal to the energy of the gap. This is the energy of the photon. When that is equal to the energy of the gap, it'll give the electron enough energy to jump from the valency band up to the conduction band. So we need to find this frequency. So F min is equal to 1.14 times 1.602 times 10 to the minus 19 to convert this from electron volts into joules over Planck's constant 6.626 times 10 to the minus 34. Solving this on the calculator, we end up with 2.76 times 10 to the 14 Hertz. Now in part B, it says what is the wavelength of this photon. So we can just use C is equal to F lambda to get the wavelength. So the wavelength is equal to 3 times 10 to the 8 over 2.76 times 10 to the 14. And solving that on the calculator, we end up with 1.09 times 10 to the minus 6 meters, which is equal to 1.09 micrometers. This is problem 11 for 1221 or 16 for 1231. In this problem, we're asked to calculate the longest wavelength of light that will excite an electron from the valency band to the conduction band. So here we've got our conduction band, here we've got valency, and we want to excite an electron from here to here. And we're asked to do this in, first of all, silicon with an energy gap of 1.1 electron volts, and then in germanium with an energy gap of 0.67 electron volts, and then finally in diamond with an energy gap of 5.5 electron volts. Okay, so we know that the energy gap is equal to the energy that the photon needs to get across it, but instead of being asked about the frequencies, in this case we're asked about the wavelengths. So we can write this as hc over lambda, and this will be the maximum lambda it can have and excite the electron from the valency band to the conduction band. So this tells us that the maximum wavelength is equal to hc over the energy gap. So for silicon, we've got that the wavelength is equal to 6.626 times 10 to the minus 34 times 3 times 10 to the 8 over this energy gap, which is 1.1 times 1.602 times 10 to the minus 19 to get it into joules. Solving that on the calculator, we end up with 1.13 micrometers, or we could write it as 1130 nanometers. In germanium, we just substitute in again 6.626 times 10 to the minus 34 times 3 times 10 to the 8 over, in this case it's 0.67 times 1.602 times 10 to the minus 19, and we end up with 1.85 micrometers. Should be a 5. Or we could write it as 1185 nanometers. And finally we do the same in diamond. In that case we just substitute in again, except for 0.67 we put 5.5. Solving that, we get 0.226 micrometers, which is equal to 226 nanometers. So part B of the question asks us, compare this with visible wavelength range, which is 400 to 750 nanometers, and hence comment on the physical appearance of these three materials. The wavelength of visible light is less than the wavelength required for silicon and germanium to excite an electron from the valence to the conduction band. So silicon and germanium are going to be opaque to visible light because they will absorb visible light as the electrons absorb it, jumping up to the conduction band. So silicon and germanium will be opaque to visible light as lambda visible is less than lambda max. However, diamond needs much shorter wavelength light to excite the electrons. So visible light doesn't have enough energy to excite the electrons in diamond, and so diamond will not absorb visible light. So diamond will be transparent as visible light does not have enough energy to excite the electrons. This is problem 12 for 1221 or 17 for 1231. In this problem, we're told that pure silicon is doped with the following elements to produce extrinsic semiconductor material. 1. Gallium. 2. Aluminium. 3. Antimony. 4. Boron. 5. Arsenic. And 6. Phosphorus. For each dopant, state whether N-type or P-type material is produced. Okay, so N-type have electrons as the carriers and P-type have holes as the carriers. So what we need to do is look for these on the periodic table to work out if they're going to have an extra hole or an extra electron. So here's silicon, which is the group 4. And we're first of all doping it with gallium. Here's gallium, so this is group 3. Which means that this has 3 electrons in its outer shell, and so it can accept another electron to be more like silicon. And so in this case it's a hole, so this is P-type. Aluminium, here's aluminium, it's also group 3. So this one here is also P-type. Antimony. Here's antimony, it's in group 5. Which means that it has 5 electrons in its outer shell, so it's got an extra electron than silicon does. And so this has an N-type. It's the extra electron, which will be the charge carrier. Boron, that's group 3 as well, it's up here. So this is P-type. Arsenic is here, which is group 5. So this is an N-type. And phosphorus is here. And so this is also group 5. And so this is an N-type. And that's how we answer that question. Okay, we're on to problem 18. This is a 1, 2, 3, 1 only problem. In this problem, we're told that the mobility, mu, of a charge carrier, electron or hole, in a semiconductor is defined as the drift speed of the carrier per unit electric field. So mu is equal to Vd over E, where E refers to the strength of the electric field driving the current through the semiconductor material. For silicon, the electron and hole mobility may be taken as mu E is equal to 0.15 meters squared per volt per second, and the hole mobility is given by 0.05 meters squared per volt per second at 300 kelvins. And part A says for N-type doped silicon with a conductivity of 4.0 times 10 to the minus 4 ohm meters inverse, calculate the conduction electron density. Okay, so to do this, we're going to need to use a number of equations. We'll need to use our equation for current. I is equal to the charge density times the size of the charges, which in this case is E, the charge on an electron, which is also the magnitude of the charge on the hole, times the drift velocity times the area. And we're considering a piece of wire here with a voltage difference delta V across it. And so we know delta V is equal to the electric field times the length of wire. We're also going to assume that this is an ohmic wire, so that we have delta V is equal to IR. So we have I is equal to delta V on R, so we can write this as EL on R. One other thing we're going to need to use is our definition of conductivity. This is our conductivity here, and we have that the resistance is equal to the length over the conductivity times the surface area. So let's substitute this into here. So we've got NEVDA is equal to EL on R, which is L sigma A. So you can see our A's will cancel out, our L's will cancel out. And what we're trying to do is get an expression for N. So we've got N is equal to sigma E over the charge on an electron times Vd. And finally, we can make use of this expression here. So E on Vd is 1 on mu. So this is equal to sigma over E mu. Okay, so now we've got the formula, now we can just substitute in. So N is equal to sigma, which is 4.0 times 10 to the minus 4, over E, 1.602 times 10 to the minus 19. In this type we're told it's doped with N, so there's a lot more electrons than holes, so we'll use the mu E. So this is times 0.15. And solving this on the calculator, we end up with 1.66 times 10 to the 16 inverse meters cubed. Part B asks us for p-type silicon. So in this case, there's a lot more holes than electrons, so we'll use this for our value of mu instead. So we've got N, just substituting into this equation here again, N is equal to sigma, 4.0 times 10 to the minus 4, with charge on the holes, 1.602 times 10 to the minus 19, times mu for holes, 0.05. Solving this on your calculator, you end up with 5.0 times 10 to the 16 inverse meters cubed. In this one, we really should have only given to two significant figures, so let's put that as 1.7 times 10 to the 16 inverse meters cubed. And actually, as this is only to one significant figure here, we better actually put this as 5 times 10 to the 16 inverse meters cubed. Problem 19, which is for 1231 students only. In this problem, we're asked for what value of the bias voltage, delta V, in the ideal diode equation, I equals I naught times the exponential of E delta V over KB T minus 1 does, in the first case, I equal 9 I naught. And so this is equal to I naught E to the delta V over KB T minus 1. Now let's cancel out the I naughts and move this 1 over to this side. So we've got 10.00 is equal to E to the E delta V over KBT. So we just need to solve the log function. We're told lower down in the question that we can assume that T is equal to 300 kelvins. So we've got log of 10 is equal to E, which is 1.602 times 10 to the minus 19, times delta V over KB, which is 1.381 times 10 to the minus 23, times 300. So we just need to solve this on the calculator now, and we end up with delta V is equal to 0.0595 volts, which we could write at 59.5 millivolts if we wanted. So that's part A. In part B, we're told that I is equal to minus 0.900 I naught. So we just go through the same steps again. This is I naught E delta V over KB T minus 1. And so cancelling out the I naughts, we end up with 0.100 is equal to E delta V over KB T when we take the log of this thing. This ends up as a negative number, so our final number is going to be negative. So we just substitute in these same numbers again, and we end up with delta V is equal to minus 0.0595, which we can write as minus 59.5 millivolts. This is problem 20 for 1231 only. In this problem, we're told that the diode shown in this figure is connected in series with a battery and a 150 ohm resistor. What battery EMF is required for a current of 25.0 milliamps? So we can work out the voltage drop across this resistor just using Ohm's law. V is equal to IR, and I is 25 times 10 to the minus 3 times 150. And so this is equal to 3.75 volts. So we've got a voltage drop of 3.75 volts across our resistor here. Now we need to look at the voltage drop across the diode. To do that, we're going to make use of this figure, which is figure 43.28 from the textbook. We know that our current is 25 milliamps. So that tells us that our voltage is approximately 0.6 volts. So we've got that this is around about 0.6 volts. And so to get the total voltage difference around the circuit, which is what the battery needs to supply, we just need to add these two together. So we've got the EMF supplied by the battery is 3.75 plus 0.6. So solving that, we get 4.4 volts approximately. This is only a very rough approximation. On to problem 21, which is another 1231 only problem. This problem asks what is meant by the terms direct and indirect band gap for a semiconductor. Sketch a simple diagram which indicates the difference. Okay, so both types of semiconductors have a conduction band and a valency band. And we can excite electrons from the valency band to the conduction band by the electron absorbing a photon with an appropriate amount of energy. Now, in a direct band gap, the electrons can jump directly from the valency band to the conduction band, as electrons in the conduction band and the valency band have the same amount of momentum. So let's write that. Electrons can jump directly from the valency band to conduction band as electrons have the same amount of momentum in these bands. So as a graph, we can represent here's our energy and here's momentum. In a direct band gap, these are lined up. Here's the conduction band and the valency band, and the electron can just go straight from the valency band to the conduction band. So this is direct. In an indirect band gap, electrons have different amounts of momentum in the conduction band and the valency band, so must pass through an intermediate state. So what we have in this case is here's our energy, Here's our momentum. Here's our valence band. Here's our conduction band. So it absorbs a photon, the electron, which increases its energy to the right amount of energy. But then what it does is it releases a phonon, which transfers some of the momentum to the crystal lattice, and that allows it to get to the conduction band. Okay, we're on to problem 13 for 1221 or 22 for 1231. In this problem, we're told that the Drude expression for electrical conductivity is sigma is equal to Ne mu, where N is the number of charge carriers per cubic meter, E is the charge on the electron, and mu E is the charge carrier mobility. In the particular semiconductor, specimen has both N electrons and P holes per cubic meter present, and the holes have a mobility mu H. Write down the expression giving the total electrical conductivity due to electrons and holes. Now, electrical conductivities just add together. So we have that the total electrical mobility is equal to the electrical mobility due to the electrons plus the electrical mobility due to the holes. So for the electrons, we've got N electrons per cubic meter. E is the charge on the electron. And we've got mu E here. And then for the holes, we've got a very similar expression. P is the number of holes per cubic meter. E is the charge on the hole, the magnitude of the charge on the hole. And mu H is the hole mobility. So that is our expression for the electrical conductivity in this case. Problem 14 for 1221 or 23 for 1231. In this problem, we're told that most solar radiation has a wavelength of 1 micrometer or less. So lambda is equal to 1 times 10 to the minus 6 meters. What energy gap should the material in the solar cell have in order to absorb this radiation? And then we're asked, is silicon appropriate? And we're given the table. So in order for this photon to be able to excite the electrons, the energy gap has to be less than the energy of this photon. So we've got the limiting case is when the energy gap is equal to the energy of the photon, which in terms of its wavelength we can write as hc over lambda. So this will be the minimum wavelength that can excite the electrons from the valency band to the conduction band. So we can solve this. This is 6.626 times 10 to the minus 34 times 3 times 10 to the 8 over 1 times 10 to the minus 6. So this is equal to 1.98 times 10 to the minus 19 joules, or dividing that by 1.602 times 10 to the minus 19, the charge on the electron, it gives us 1.24 electron volts. If the gap is larger than this, then a photon with this wavelength does not have enough energy to cause the electron to jump from the valence band to the conduction band. So the band gap for silicon, we're told in the cable, is 1.17 at 0 kelvins or 1.14 at 300 kelvins. So this energy is greater than this energy. So this photon does have enough energy to cause an electron to be excited in silicon. So we can put the energy gap needs to be less than 1.24 electron volts, and that silicon is an appropriate material. And that's the end of the 1221 problems. Okay, on to problem 24, which is 1231 only. This is problem 24, which is a 1231 only problem. In this problem, you're told to assume you are to build a scientific instrument that is thermally isolated from its surroundings, but such that you can use an external laser to raise the temperature of a target inside it. Since you know that diamond is transparent and it won't let gas molecules pass through it, so you can have a strong vacuum inside it, you decide to use a diamond window in the apparatus. Diamond has an energy gap of 5.5 electron volts. Okay, so let's write that down. The energy gap is equal to 5.5 electron volts and between its valence and conduction bands. What is the shortest laser wavelength you can use to warm the sample inside? So to warm the sample, the wavelength needs to be able to pass through this band gap. So the energy needs to be less than in this band gap so that it is not absorbed by the diamond. So this is equal to HF, which is equal to Hc over lambda max. If we have a wavelength less than this wavelength, then it will have enough energy to excite the electrons and so it will be absorbed. So let's solve this. We've got 5.5 times 1.602 times 10 to the minus 19. This is just converting this energy in electron volts into joules by timesing it by the charge on an electron, is equal to 6.626 times 10 to the minus 34 times 3 times 10 to the 8 over lambda max. Solving this on the calculator for lambda max, we get 2.26 times 10 to the minus 7, which is equal to 226 nanometers. So we need the wavelength to be greater than 226 nanometers to ensure that the photons don't have enough energy to excite electrons from the valence band to the conduction band in the diamond, which will mean that these photons can pass through the diamond unimpeded. Okay, we're on to the extra problems now, which are only for 1, 2, 3, 1 students. So starting off with E1. We're told that a driver claims that his car won't go fast at night. The car has two 60-watt headlights, so 2 times 60-watt headlights. These emit photons in the forward direction with a typical wavelength of 500 nanometers. So lambda is 500 nanometers, and here are his headlights emitting these photons in the forward direction. What backward force do these exert on the car? Okay, these are going to exert a bit of a backwards force as the photons have momentum in the forward direction, and so there'll be an equal force backwards on the car. So we know from impulse that force times time is equal to the change in momentum. And we also know that the energy of the photons is equal to Pc, where P is their momentum. So we have that force is equal to the change in momentum over time. Now, initially they have no momentum and then they have momentum P. So we can put this as E over Tc. Now the energy over the time, that's equal to the power, so this is P over C. And the power these headlights have is 2 times 60 watts, so this is equal to 120 over 3 times 10 to the 8. And so this gives us force of 4 times 10 to the minus 7 newtons. A tiny, tiny, tiny force. And then the question goes on, what extra power is required to overcome this at 100 kilometers per hour? So the power, we've already said, is equal to energy over time. Now, energy, this is the work that you need to do to overcome this. So this is Fx over t, and x over t is the speed, so we've got Fv. So now all we need to do is substitute in. Our force is this force here, 4 times 10 to the minus 7. The speed is 100 kilometers per hour. So to get that into meters per second, we times by 1,000 and divide by 60 times 60. And so this gives us 1.1 times 10 to the minus 5 watts, a tiny amount of power. And it says compare this with other effects that might reduce the car's top speed at night. Well, the most obvious one is that the car is now expending 120 watts to light these headlamps. So that's massive in comparison to the power it needs to do to overcome the momentum of the photons from the headlamps. So car is using power to light the headlamps. That would be the main effect. There are other effects that you could consider as well, like at night it tends to be cooler, and so the atmosphere is more dense, and so there's more air resistance. But at night, because it's cooler, you won't put on the air conditioner and you won't open the windows. So there's a few other facts you could consider as well, but this is probably the main one. Okay, problem E2. In this problem, we're told that an aluminium sphere, freshly polished with sandpaper to remove the oxide layer, has a radius of 100 millimeters. It is illuminated by ultraviolet light with a wavelength of 150 nanometers. What is the maximum charge that will be developed on the isolated sphere? The work function for aluminium is equal to 4.08 electron volts. Okay, so we've got these photons coming on. They're exciting electrons. Let's start by working out what is the maximum kinetic energy that the photons could have coming off this sphere when the sphere is uncharged. So in that case, the energy of the photons going in is hf, and this goes into the work function, and then the rest can go into kinetic energy. So we have that the maximum kinetic energy they can possibly have is equal to hf minus phi, which is 6.626 times 10 to the minus 34. Now f is given by c, which is 3 times 10 to the 8 over lambda, which is 150 times 10 to the minus 9. And then we've got to subtract off our work function, which is 4.08, and this is in electron volts, so getting it into joules, as this is in joules, so times 1.602 times 10 to the minus 19. And so this is equal to 6.71 times 10 to the minus 19 joules. Now, this is the kinetic energy that these electrons will have when this sphere is uncharged. However, as it loses electrons, it becomes charged. And so we have a potential difference that the charges have to pass through to escape from the sphere. So at a big distance from the sphere, the potential is equal to 0. At the surface of the sphere, it has potential, let's say, V. So what we need to do is work out the potential difference between V and this V equals 0 out here, and then this energy can go into getting the electrons, overcoming that potential difference between the surface and V equals 0. So we've got V is equal to minus the integral of E dr, where this is the electric field on the surface of the sphere, and we're going from radius r, which is the radius on the surface of the sphere, out to an infinite distance, so infinity. And so substituting in, we know that E, the electric field, is equal to kq over r squared on the surface of a sphere. So we can write this as minus 1 over 4 pi epsilon naught, that's the k, times the q, times the integral from r to infinity of 1 over r squared dr. And so integrating, we end up with minus q over 4 pi epsilon naught 1 over r from infinity to r. And we've got a negative sign here. So this is equal to minus q over 4 pi epsilon naught 1 over infinity 0 minus 1 over r, so that's minus 1 over r, so we've got 1 over r. So this is equal to q over 4 pi epsilon naught r, with the voltage on the surface being negative and the voltage out here being 0. Okay, so we know that the energy that you need to overcome this potential difference is just given by the voltage times the charge, and it's a negative charge, so our negative signs will cancel out. So we've got VE is equal to QE over 4 pi epsilon naught R, that's just multiplying this by E, and this is equal to this energy here. This is the energy that can go into exciting the electron. So 6.71 times 10 to the minus 19. And so solving this, we want to find out what Q is. So Q is equal to 6.71 times 10 to the minus 19 times 4 pi times epsilon naught, which is 8.85 times 10 to the minus 12 times the radius, which is 100 times 10 to the minus 3, and then we divide all of this by the charge on the electron, 1.602 times 10 to the minus 19. And solving this, we end up with 4.66 times 10 to the minus 11 coulombs, so we can write this as 47 picocoulombs. And so that's how we can solve this problem here. Problem E3. In this problem, we're asked what would be the wavelength of the least energetic photon that you could feel as a collision if it were absorbed by your finger. Determine the required energy experimentally by dropping small objects from known heights. Okay, well, let's assume you drop a 1 gram mass, 1 centimeter, and can just feel it. Well, the energy in that drop is given by the gravitational potential energy, so mgh. So this is equal to 1 times 10 to the minus 3 times g, which is 9.8, times the height, which is 10 to the minus 2. And so this is equal to 9.8 times 10 to the minus 5 joules. Now we're asked to find the wavelength of the least energetic photon. So what we need to do now is equate this to the photon energy, which is equal to hf, which is hc on lambda. So we have 6.626 times 10 to the minus 34 times 3 times 10 to the 8 over our maximum wavelength. We need to have wavelengths less than this so that the photons have more energy, and this is equal to the 9.8 times 10 to the minus 5, which tells us that the maximum wavelength the photons can have is 2.03 times 10 to the minus 21 meters. So that is a very short wavelength. And then we're told to compare the energy and wavelength for such a photon with the value of the most energetic photon ever measured. Cosmic gamma rays sometimes have energies of 100 tera electron volts. So we have that the energy is equal to 100 tera electron volts, which is 100 times 10 to the 12 electron volts. And so let's work out the wavelength of this photon. So this times 1.602 times 10 to the minus 19 to get it into joules is equal to hc over lambda. And so lambda is equal to 6.626 times 10 to the minus 34 times 3 times 10 to the 8 over 100 times 10 to the 12 times 1.602 times 10 to the minus 19. And solving this, we end up with 1.24 times 10 to the minus 20 meters. These are actually very comparable. So there are photons which you could actually feel hitting you. Problems E4 and E5 are left as an exercise for you. These are fun, challenging problems, and it's beside the point to have somebody talk you through how to do them. So read over those carefully, have a careful think about them, and hopefully you'll find them quite challenging and rewarding.